Hi, my name is Gary Zahn, and I'm a first-year mechanical engineering student. Before I go to talking about my Arduino Smart Car, which is my electronic project for today, I'll first go through my backgrounds in terms of programming and hardware. So as you can see here, I have C++, Python, Java, and MATLAB, and I have also experience in circuits as sensors, which means capacitors, resistors, and some parts of AC circuits, and many more knowledge surrounding these circuits. And I am also somewhat experienced with microcontroller, and to be more specific, Arduino. Um, let's first, so for Arduino, the main logic that's surrounding Arduino Smart Car consists of core DC motor control, obstacle detection, and collision avoidance. And this project was actually collaborated. It was actually a collaborative project between me and my friend, essentially because um, of the situation given by COVID-19. We were not able to, currently, I was not able to uh, acquire the model at hand right now, so I have to show you photos, and I'll show you the photos of the model right now. So here's a model. As you can see here, there's four DC motors, and there's a battery, there's the Arduino IDE board, and we have another board there. Down below between the chases, it basically essentially helps the remote control the car. And these are just different views of the car here, and then here's the HSC04 microcontroller, and that's it for the overall model. And I'll be now moving on to the code, which is the most important part of the project. Okay, now let's move on to the coding aspect of the project. The top part, so these parts are just initializing the different pins. So we initialize the wheel channel pin, we initialize the control signal pin, and we initialize the trigger and echo pin, and it's used in the algorithm to it's used in the ultrasonic sensor, and it's used for collision avoidance. And we can see that we made the default distance to be 0.3 and the default velocity to be 0.5. The reason why we did this was because we were testing the model with different types of distance and different types of different numerical values of speed. And we found that these two values matched the best together, as they were just base values. There was like the lowest possible values that the car can go without just like not moving. Now let's move on to setup. Setup, we are just enabling the IIR control. We are also um, assigning the pins to all output, and here we're just activating the channel pins. So for left wheel and for right wheel, and then we're also assigning the trigger and echo pin, trigger pin to output and echo pin to input. Now let's loop the loop. The loop is basically our main method. And you can see here through our testing, we were able to find that the maximum velocity is 0.676 centimeter per second, and the maximum angular velocity is 336 degrees per second. Uh, uh, for equations like power or equations like degree down below, we were able to find it through mathematical calculation. So basically we just plot the data points of what degree, how many seconds it takes for, let's say, 90 degrees to spin, or how many seconds does it take to move 1 meter, no, 1 meter, basically, and that's how we found the equations. As you can see here, we're just initializing, we're just, through that equation, we were able to find power. And here you can see we were setting speed. And that's it. Now let's move on to one of the main aspects of the code, which was the remote control. So let's So the remote control, as you can see here, there's four different controls. There's upward, downwards, right, left, and essentially once it's pressed, the CMD value is just the value that gives from the remote control. And there's forward, backward, right, left. As you can see there, it's kind of different as this part's distance and this part's degree. And these are just values that we have set initially. So degree is 90 degree, and distance before was 0.3. And as we do it, we can change it according to the liking. And then we also have a pound key. Pound key is essentially changing. It allows the user to change the distance that the car moves by, and the asterisk keys allows the user to set the speed, adjust the speed according to their liking. So by corresponding to the numeric value, we were able to assign that distance to 0.1, distance to 0.9, and we're also able to assign the velocity to their choice. These are just increasing, these are not actually 9 meters per second, it's just increasing the velocity according to, so there's different levels of speed, so each one's higher than the other. Okay, and here we have set speed. Set speed, it was used essentially when in the beginning for here, and then it will be used in future. It's basically just controlling the power output. It outputted into the channel pins, which as you can see, if you've forgotten, it's here, wheel channels. So here and here, and high means the maximum. Okay, forward. Forward is a very important function because essentially it's the part that we use for algorithm. It's the part that we use for obstacle avoidance, and that's because the HCSR04 sensors at the front, so therefore it's only detecting the movement of the car and avoiding collision at the front of the car. It will not be able to um, not be able to detect the the movement of the car at the when it's moving backward, as it's basically analyzing the movement of light rays and seeing how it reflects off the object onto the sensor again. Um, so we have targeted time. Targeted time essentially because in Arduino we're not able to input in the distance as the Arduino distance is quite different from the actual distance in real life. So therefore we need a targeted time. Culminated time is just the time that we're using to count like the time traveled so far. Um, Obstacle distance means this is the obstacle distance is the variable that we're using to check for the amount of distance between the car and the object. Let's for example the wall. And we have stop time. Stop time should be 0. Start times, a millis is essentially is like a stopwatch. Like it starts from 0 and just keep on going. So when when the car starts moving forward, and here we're just turning it on, allowing it to move forward. Culminated time is the current time, basically while it's less than the targeted time, um, where we're allowed to keep on moving, and we're just updating the culminated time continuously. And because here we're every time we go into the while loop, we're just checking for the time it takes for it to stop, essentially, um, and we're just subtracting it to change the culminated time for the amount of time that passed. And this while loop, we're just using it to find if the obstacle distance is less than 0.11. That's like in the reach of 11 centimeter from the object. Okay, and then if it is less than, then it's true. So we have to stop it. So once the while loop finish executing, essentially what we're doing is we're just stopping the car. And if the car was stopped, we're just essentially calculating the cumulative stop time and just resetting the car stop value to false. It's just here. As we're going to have to repeatedly reuse this function for future when we use the forward function again. As you can see, backward we don't have this whole this huge amount of code. We just have using the distance. We're using we're using the d equal vt equation, and we just find the time it takes, and we're just delaying it with the amount of time, and yeah, and then we just stopping the car right there. Left and right are somewhat similar. So this equation, as I said before, we use mathematical methods to find the equation that's suitable to convert real life degrees into time. And through time we were able to delay it. And after the delay time is done, we're just essentially stopping car. Another very important part of this the turning function is that it doesn't the power that inputted the current power that the car is at does not matter, because we're always setting to 125, as when you turn you want it to turn slowly, as if it turns quite fast then it might flip over. Stop car is just turning them all to low, just essentially just stopping the output to the pins. And we got a pin time function. It's just essentially this is a very important function, as it uses the HCSL4 sensor. It just checks for the time it takes to bounce signal from the object back to the car, and it's using the light wave. So we're first just having the trigger pin start out low, and then we're delaying it through 20 microseconds. We're just seeing how long it takes. So we turn it to high, and then we turn it back to low, and we're just seeing how reads how long the light wave takes to bounce back. And then here, as you can see, calc distance. This was used here. Obstacle distance equal calc distance. Essentially, this distance uses this function that I've talked before. It uses it, and it just converts the pin time that we have gotten, and then we're just converting it into distance from the sensor, or just converting the distance from the sensor to the obstacle distance from the car. These are irrelevant functions: calf, calb, cal l. These are just testing functions that we use to derive the equations that you see here. So here, the one we used here for time, and then the one we use at the top, I think we use it to convert for power. So here. So that's it for the logic side of the model, and I'll now look into the final video, and it's just a live demo that my friend has recorded, and I'll just show you right now. Now let's move on to the car demo. So you see here, my friend pressed the pound key upwards to so this it should be moving at 0.3 meters, and you can see it turning by 90 degrees with the left and right key. Overall, the result of the project is very well, as the calibration that we have done and the function has worked out very well. And that's it for the project. But lastly, I want to thank the project manager for looking through this video. I hope you enjoyed it as much as I did, because I really enjoyed this project. And thank you for watching.